So it's a great pleasure to have Yannick here today from Johns Hopkins University. So Yannick will talk about parabolic gluing and construction of blow-up solutions. Thank you, Yannick.
So thanks a lot for the invitation, the remote invitation. So I'm going to talk about something that I was working on like in the last few years. And which is basically kind of basically proving like some rigorous theorems after like justifying some matching asymptotics that physicists have been doing for the last decade. So basically, so let me try to put that a little bit in perspective. So the idea, the goal is to construct like blow-up solutions in some parabolic. I will mention some other types of equation problems in finite or and infinite time. So by constructing blowing up solutions, I mean like proving. I mean, typically I want to have like to prove the existence of a solution, which is like a main approximation, which is like the main order and gives like the form of the blow-up, plus something, another function which has some behavior. And so it's really like, it's not a criterion for blow-up, okay? And it's much more precise than a criterion. So of course, like, as you know, like a classical theory is that you have a dichotomy between blow-up in finite time and global well-poshness. Okay, I'm not talking about smoothness here. And in infinite time, you have either convergence. So this is what happens on for the Yamabe flow on closed manifolds in positive time, or you have blow up in infinite time. So this is what happened generically for on harmonic map flow for positively curved targets, or the Fugitive Equation. I will. So the semi-linear heat equation. And I will mention some results about that. So basically, the idea is that of the method is very much related to what people in geometry or geometric analysis have been doing for decades, which is gluing method. And so in this case, this is some kind of parabolic version of gluing. So the idea of parabolic gluing is just like you have two regions, basically, an inner region where you are close to the blow profile and an outer region, and you try to glue them, okay? This is like when you do matching asymptotics, like formal expansion, this is exactly what you look at, right? So this type of gluing in particular, inner and outer, because there are several in elliptic problems, it's when you, in elliptic theory, it's like when you want to produce concentrating solution on a higher dimensional submanifold, so for example, a curve, not blowing up at a point, not concentrating, sorry, at a point. And so as I was mentioning, for parabolic problems, this is like finite or infinite time blowups. So the idea is the following. So you start with a good approximation of the solution, which is a candidate to blow up. So if it's a good approximation, hopefully it will give you a small error in the sense that if you plug it into the equation, it will give you like a small term. And then you rectify the error, right? Or you rectify the approximation, sorry, by an inner region where you are like, so phi is like in some good variables, your candidate for I mean, it's a region which is, it's a function which is supported close to the blow-up point, and an outer region which is basically the rest, okay? And you have stretching variables. So it's going to be more clear on some examples. And so basically you have like a coupled system between the inner and the outer region, okay? Okay, so let me try to go more precisely into, I don't know why, okay. Okay, so what I call the Fugitive equation is the gigaton equation, basically. So you have like a semilinear equation in Rn here, and you have two types of blow-up. The one given by 0D, okay, has the same scaling. This is like the blow-up type 1, and the type 2 blow-up, which is all the other, okay? So Fujita studied this equation according to the size of the initial data and the exponent p. You have like either existence of a finite time blow-up or infinite time blow-up or global existence, okay? So motivated by this work of Fujita in the mid-60s, actually a lot of work has been developed to understand what types of blow-up you can develop for this equation. And there are some here. The first really like, how can I say, very like seminal and detailed analysis was done by Giga and Kohn in the mid-80s and after. And so basically, what you can prove is that if you are subcritical and if you are in a convex domain, if you are, so you have only type 1 blow-up. But if you are subcritical also, you can blow up at multiple points. So you can blow up like at multiple on the domain. Okay, you can concentrate at multiple points in the domain. And actually, like when you are critical, which is harder critical for Sobolev, only type 1 blow-up can occur. All of these are for positive solutions. And it's been proved several like types of solutions have been constructed by this. So what I would like actually to discuss are this type of blow-up solutions in the case of geometric equations, okay? So geometric flows. So I will basically consider two flows, but actually it shares a lot of similarities with other types of flows. So the first one is the harmonic map flow, and the second one is a variation of it, which is like when you have a Neumann free boundary condition. Okay, so let me say like a few words about harmonic maps. So I will consider only when the targets are spheres. So an harmonic map is a critical point of the following conformally invariant into the functional. And the major issue, the major issue for this problem is the regularity, because the equation is critical, okay? I mean, like the weak solutions, H1 solutions give rise only to an L1 right-hand side here for the equation. So for the equation, so for critical points in general, this is very hard. So there have been like many works of many people. And in 2D, you can prove by Hélin that you have full regularity of critical points. So there is no partial regularity. And in higher dimension, depending if you are minimizing or stationary, you have partial regularity. Okay, so you have the existence of a singular set. And if you are a general critical point, Rivière constructing a famous example where you have like a weak harmonic map, so weak solution of this equation, which is discontinuous everywhere. So you need to assume more to have a regularity in higher dimension. So to construct harmonic maps, basically the most important, the first work was a work by Ilse and Sampson, where they looked at heat flow, right? So you look at the gradient flow of the harmonic map functional, right? And so basically, so if you are in a domain, for example, of a Riemannian manifold, or even like a domain in Rn, you give yourself a data, right? which is of course like satisfying a compatibility condition with the initial data on the boundary. And you look at the heat equation, the gradient flow of your function, right? So you have exactly this. So it's been introduced by Illes and Sampson, not when the target is, well, when the flow itself has been introduced by Illes and Sampson, but they prove like convergence of the flow and global existence whenever the target is negatively curved and or non-positively curved. And of course, like when you converge, actually you converge when to an harmonic map. Okay. But the problem is that when you are positively curved, you might not have convergence, okay? And you might not have even regularity, global existence of smooth solutions, okay? So in the case of the sphere, for example, Unmei Chen constructed by Ginzburg-Landau approximation, an harmonic map, which is like a weak solution of the harmonic map flow, and Chen and Struve looked at the partial regularity of this weak solution, and so on. I mean, there are many works. The best Bible for that is the book of Wang and Lin. For an up-to-date, at least like for in the smooth case and the Riemannian case. So an important problem related to ours actually is the blow-up analysis. So the singularity analysis, how the flow, right? Or actually, like it's not only something that which is specific to the flow. It could be like done also for the elliptic system, is to understand how you a singularity appears, right? So, so the following, so at the first time, okay, where the continuity of the solution breaks, right? You have the following decomposition. So it's due to many people. Actually, this is a parabolic version of a global compactness result of Struve, actually. So you have a sequence of times going to the block time where basically you can decompose your solution in this way. So you have like U star, which is a nice function, H1. And then you have the obstruction to compactness, okay, which is given only by bubbles, right? So basically entire solution, UI, of the stationary equation, okay, centered at points QI, okay, and stretched, okay, by sequence lambda I, okay, and you have a finite number of bubbles, okay. So what are these UI? Well, these are finite energy entire harmonic maps, okay? So this is a global solution, an entire solution of stationary solution. And actually the thing is that in the case of the plane into the two-sphere, which is the case I'm discussing now, it's been completely classified by complex rational functions and conjugate of them. And you have even like a quantization of the energy, okay, for all this. Okay, so basically what the singularity analysis tells you that the density, right, gradient U square, here I should put like I forgot to put the measure, yeah, okay, the Lebesgue measure, along a subsequence, right, is going to the energy of an harmonic map, right, a smooth harmonic map, and 4 pi mi, right, this is like the quantization property of entire solutions, Dirac masses at all the points where you look. So it's a pretty precise description of the way you bubble for your flow. So Topping proved that the blob rates, which are actually this lambda I, right? Lambda I depends on time, okay? Sorry, is actually like little o of the square root. Okay, so it's not a type 1, okay? It's type 2 blow up. So of course, like here I describe only for when you have finite time, right? But the same type of decomposition occurs in infinite time. You have like the same type of formula, okay? Okay, so now, what can, besides having this, so the whole point of the singularity analysis, of course, well, the whole point. The first assumption is, let's assume that we have a time where the continuity breaks, okay? Well, in this case, sorry, then you can raise the question, well, but can I prove that indeed I have such a time, right? Well, the first example that I'm aware of is due to Chang. This is not Alice Chang. This is Casey Chang, I think. Ding and Rogandieu, who proved that constructed an explicit blow-up solution. Okay, they constructed an initial data and a boundary data. Okay, phi, such that you can prove that the solution blows up in finite time. Then many years after, Raphael and Schweger constructed in a more general, I mean, in the co-rotational setting, so in the symmetric setting, when you are a priori assuming symmetry, constructed like another blow-up solution. And actually, the best result that I'm aware of at the moment is like a paper by Davila, Del Pino, and Wei, where they constructed general blow-up solutions, right, in a non-symmetric case, so away from the symmetric class. Raval and Schweyer were assuming that the initial data is symmetric, okay? So so they are taking their solution a priori to be symmetric, okay? The thing is that what Davila, Del Pino, and Wei is that they constructed indeed a blow-up solution, okay? But in the more general case, without any symmetric assumption, okay? But what they prove is that the way you bubble is like an equivariant map. Okay, so so let me come now to another version, a variation of the harmonic map flow, or the harmonic map system, which has half harmonic maps on Value and Rivière. So basically, they introduced, like, they were interested by understanding some compensation compactness phenomena in odd dimensions, and they introduced this functional in 1D. Okay, and it happens that this functional is invariant under the Mobius group, which is a trace of a conformal map keeping invariant half space. And actually, when you write the equation of this functional, and the target is a sphere, right, you get like a critical equation exactly in the same way as before, right? This is complete analog of this equation that I wrote here, right? Except that I take delta to be delta 1/2, and instead of having gradient Q square, I have like one piece of Gallardo norm, right? Only one integral. So this term is L1. in general. And so you could ask, well, okay, can I construct blow-up solutions, right, for such flow, right? The harmonic map, the gradient flow of this map. Well, the answer is yes. Well, first I need to have the answer is yes. And first I need to introduce the same tools as I had before, which are global harmonic maps. Here I will take the target to be S1, the circle, okay? Just to simplify, but the construction should hold when the target is higher dimensional. So I prove with Mio that if you take so first, if you remember the previous slides, I need to understand what is like a bubble, okay? And in the case of the heat flow of standard harmonic map, the bubble is an entire harmonic map from the plane into S2, okay? So here I need to classify, if I can, entire, so on the whole real line, half harmonic maps into the circle. Well, you can do it also. This is like a finite Blaschke product. And you have also a quantization, okay? So it's very parallel, except that it's explicit, right? I mean, like in degree 1, okay? D is actually the degree of the map. So in degree 1, so k equal to 1, okay? D is not a dimension, this is a degree of the map. K equal to 1, you can describe what is one of these bubble, and this is exactly like in the standard case, like a stereographic projection, or the inverse of the stereographic projection. Okay, and actually it's non-degenerate in the sense that the linearization of the harmonic map equation, right, this equation around this bubble in L infinity is spanned only by the invariances of the equation. So it's not degenerate in this sense. So what we proved is the following with Wei and Zheng is if you pick k points on the real line, then you can construct initial data and a sequence of k-smooth functions, right, which are actually converging in time to the point where you got a bubble, okay, and rates, okay, mu jt, okay, which are actually exponentially small when t goes to infinity, such that this problem has a solution of this form. So this is like, well, you have to fix like a pole, okay? So you have like a sum of bubbles plus something which is going to 0 when t goes to infinity. So you see like what is the profile, right? When t goes to infinity, you are like concentrating, so you are building really a solution blowing up, right? You are concentrating close to one of these points, okay? And the profile that you have is an entire half harmonic map from the real line to the circle. Okay, does it make sense? Okay. So okay, so this is like what I meant originally when I wanted to have like when I said like I wanted to have like a precise description of a solution, of blowing up solution. Okay. Okay, so I will explain a sketch of the idea. Let me mention like an interesting fact about this flow. So this flow is the gradient flow of the Dallio-Rivière functional, okay? the thing is that, well, at least like a gradient flow, I should say, of the Daillot-Rivière functional. The thing is that there is a strong analogy, which is actually related to geometry, among other things, between this functional in 1D, okay? So the fact that you have the real line here and the power 1/4, and this functional in 2D, okay? The fact that you have a gradient here and a domain in the plane. Well, this is alluded actually in this sentence that the functional is invariant under the Mobius group. So the thing is that by analogy, okay, so this flow should have a lot of analogies, particularly qualitatively, with the harmonic map flow in 2D, right? The thing is that in the harmonic map flow in 2D, Chang, Ding, and Ye proved that there is, sorry, let me write the flow again, there is finite time blow up, generically somehow, like cannot rule it out easily. Okay. Well, actually some formal computation that we did with Junchen Wei and Yuan Zheng, which are like the natural one if you are looking for finite time blow up, okay, are suggesting that you never have finite time blow up for this flow. But actually we don't know how to prove it. So in other words, okay, you would have like a global smooth solution of this flow. And we don't know how to prove it, actually. But some formal computations like suggest that there is no finite time blow up. There is only infinite time blow up. Okay. So I will explain, I will sketch a way, the idea on how to construct those solutions. But let me, before going to this part, let me introduce like a connection with this flow, but which is a variation of the harmonic map flow, and which is a harmonic map flow with free boundary. So now you consider like the following question. Instead of considering an harmonic map from a closed manifold into a closed manifold, you consider like an harmonic map from a manifold with boundary into a closed manifold, okay? So M has a boundary, okay? And you are taking N, so N is a target, okay? Which is like a manifold without boundary. Okay, so now, of course, like if you want you have to take into account the fact that you have a boundary for your domain, okay? And the thing is that if you take a continuous map from M into N, which is satisfying the fact that, which is such that the image of the boundary of M is in the submanifold of N, which has also no boundary, it defines a relative homotopy class, okay, in maps from this space into this space. And so you will say that these two maps are homotopy, of course, if you have like a continuous in the homotopy, but in the usual sense of that, like the image of the boundary is staying into the submanifold sigma. So, in other words, actually, if you look at what is the variation of this problem, gamma is the second fundamental form of the embedding from N into R into a space, an Euclidean space. Okay, it's a smooth closed manifold. Okay, and so you get like an harmonic map type equation. Okay, so an equation which is quadratic growth in the gradient. But of course, you have like to take into account the fact that the domain has a boundary. So you have a boundary condition that you want the map of the you want to map the boundary of M into a closed manifold sigma. And actually it comes with a free Neumann condition. And you can see that geometrically it tells you that du d nu, the Neumann derivative, has to be orthogonal to the tangent at U of sigma. So geometrically, you see, like you have like a map, you have a manifold M, you have a target N. In the target N, you have a submanifold sigma, right? And you are constraining, right, your boundary of the domain to go into sigma, right? So this is a general form of what is known as harmonic maps with free boundary, which has been known for a very long time and appears actually in a lot of problems in geometry. So you can introduce a flow, right, which is known as a harmonic map flow with free boundary, which is exactly analog to the flow of the heat flow of harmonic maps, right? This is a natural parabolic flow. And now you could ask, well, why do I introduce that, right? Well, I introduce that because actually there are interesting connections between half harmonic maps, okay? So this functional here, sorry, okay? And this system here. And the reason why it's so, it's because if you take an harmonic extension of a half harmonic map, okay, in the sense of Dahluen-Rivière, you get like an harmonic map with free boundary in this sense. Okay. So somehow, but this is now something which is pretty well understood, right? If you have a nonlinear Neumann data, which is here, this is highly nonlinear, right? If you have a nonlinear Neumann data, then you have basically a non-local problem, right? And so tools of non-local equation has been used to actually prove some regularity result. For example, you can look at the papers by Fraser and Shane, where they look at extremal metrics for the Steklov problem. Okay. So basically, this flow that I was mentioning, the harmonic map flow with free boundary, has been studied by Struve and Chen and Lin. And in particular, Chen and Lin raised the following question: whenever you have like a smooth domain, okay, in R2, your n, the target is Rn, okay, so this embedding this equation is trivial, right? What is non-trivial is the submanifold sigma, which is in Rn, okay? Can I construct a smooth initial datum such that I have no global solution? Okay, so it blows up in finite time. So in this setting, okay, the equation is exactly this one. In the simplest setting, the equation, so that Chen and Lin were mentioning, the equation is exactly this one. I have a heat equation in the half space, okay, half plane. I'm targeted into S1, okay, and my Neumann derivative, okay, which is just du d nu du dy, right? No, it's minus. Is orthogonal at the boundary, so on the real line, to the tangent of S1 at this. Okay, answer to to the question of channeling is true. So, well, it's yes, I should say. So one can indeed construct like such a non-trivial blow-up solution. Okay, so you pick k points. So this is the same type of statement than I said before, right? For the harmonic map equation, half harmonic map heat flow. So you pick k points on the boundary. So of course, like here, if you blow up, right? By blowing up, I mean, like if you have concentration, right? It cannot occur inside. You have a heat equation inside, right? So it has to go on the boundary. Okay, and if you take a sufficiently small time, okay, you can cook up like an initial data such that you're going to blow up exactly at these k points when you reach capital T. Okay, and so you have a decomposition which is exactly of the type of the one that I was mentioning before, and here you see like you have this kind of log type rate, okay, of blow up in time, and omega is exactly the same omega as before. So this omega, which is this omega, and which is an entire solution of a half harmonic map. And why did we manage with Johnson and Yuchan to do that? Well, we managed to do that because we could actually, what kind of which made this question tractable is the fact that this very nonlinear, this nonlinear condition can be expressed into like a non-local operator, because this problem is actually equivalent as taking the square root of the whole heat operator, and now your nonlinearity becomes that. So now, by analogy, right, you are kind of happy because, like, you see, like, if you were like forgetting the square root, and if you were taking, or if you put, yeah, if you were forgetting the square root, in here you are getting rid of integrals, you would have something which would like indeed the harmonic map heat flow, the classical one. Well, this is a 1/2 version, okay? And this is another instance, actually, where we could, the thing is that because of my classification with Mio, right, we could like, actually more like, and also because of this analogy, which is another instance of the Caffarelli-Silvestre extension, okay? We could, so using non-local tools, we could run the gluing. So somehow these problems, I mean, this problem in particular is in between the 2D harmonic map flow, the classical one, harmonic map heat flow, and what I call the half harmonic map flow, which is this one, right? Which is this one. However, notice that the stationary solutions of this flow and the harmonic map flow with free boundary are the same, right? They are half harmonic maps, or up to taking the extension, they are harmonic maps with free boundary. Okay? So this is just a different flow, right? Okay, but they share a lot of features. Okay, so okay. So before like giving you like explaining like a sketch of the proof for the first flow, right? The half harmonic map flow. Let me discuss a little bit like this type of problem. Well, actually, it's going to be a little more clear, seeing like the sketch of the proof. But the method is kind of very versatile, can be used in a lot of parabolic problems. So, for example, well, next week, like Juan Davila, the One Word PDE seminar, will talk about one of these instances, but you can apply for a lot of parabolic problems, say in particular geometric ones. So, for example, there is an extremely nice paper of Del Pino. Actually, because you can figure very quickly that this is not the good enough approximation, so you need to improve it, right? You need to improve the error. And so basically you cook up like a better approximation away from the blow-up point Q, okay, by adding a small term. And now what you get, right, is you rescale variables, right? And you get this type of system, okay, that you can solve. And using the fact that since you have like L omega is just the linearized operator, right, here, okay? Well, U is little omega, I have changed variables. So of course, like for this system to make sense, right, you need to have like this is in the satisfy an orthogonality condition, right? Okay, because L omega has a kernel, right? And the kernel is okay. So you test this with the invariances, the vector field generated by the invariances, right? And then it allows you to fix all of this, the mu of t, right? And at the end of the game, what you need is to show that this function will solve this equation, right? So you have like, I mean, this is, I mean, you see like if you test for Z3, which is the third invariance, right? In the L2 sense, then you figure that mu naught, okay? So the first order of mu of t has to be exponentially small, right? And if you test the error with Z2, the second invariant, you get like the fact that psi prime of t is equal to 0, it's a constant. It gives you like some compatibility conditions to have a good error, right? But of course, these are first order. You have to add something, right? Okay, so you plug once again, and now you do the inner-outer gluing. Now you have a good approximation, and you do the inner-outer gluing. Okay, so what will be the inner-outer gluing? Well, you take a cutoff, okay, close. So psi of t is close to the blow-up point. Huh? By blow-up point, I mean blow-up in space, okay? Okay, so you take like a function eta, which is cut like, I mean, like supported on the neighborhood of this blow-up point, right? Okay, so this is an inner outer contribution, right? Inner because you are close to a blow-up point, outer, well, because you are far away. And at the end of the game, again, what you get is two coupled systems. Okay. So you want to solve this coupled system. Okay, system of sorry. Here, you solve first the outer. Okay, 17, and with the function phi fixed. Okay, and then it gives you the solution of the outer as a function of the inner, and you plug into the inner. Right? Well, but the thing is that to be able to do that, you need to have a good linear theory, in the sense that you need to construct like nice solutions of this problem when H has some given decay, right? And this is like what you can do. The thing is that it's a parabolic system, right? It's a parabolic system. The problem is that here the operator is quite complicated because the operator is basically a half Laplacian plus things, right? Lower order terms, right? But okay, but in particular, like the half equation is solved like explicitly by the Cauchy law, right? So you have an explicit fundamental solution, right? So you can derive estimates, okay, weighted estimates actually, and this is a way you solve this is the way you solve the outer, right? And then you end up with solving the inner, right? And this gives you this type of thing, and you need again a good theory in weighted spaces, and the fact that you need solvability conditions, right? Because you have a linear operator here, and you have a right-hand side, and this operator as a kernel. So you need like the compatibility solvability condition, but it will allow you to solve in psi and lambda. Remember that it's psi 1, I think, the way I wrote it. Yes, psi 1 and lambda, right? These are unknown functions also. So it's so why is all of this kind of parabolic in nature somehow? It's because it's very important for the scheme to have like a good estimate, good regularity estimate. It's not enough to solve in phi. You need also gradient estimate of this problem. If you were looking at, for example, the energy critical wave equation, or even energy critical Schrodinger equation, then you have regularity issues, right? Well, for wave, you have regularity issues, and for Schrodinger, right? If you take the Schrodinger equation, I d tau phi equal to L omega phi plus H, right? The fundamental solution of the Schrodinger equation does not decay. This is exponential. I mean, the Schrodinger operator is the Schrodinger propagator is unitary, right? So you have no decay in space. And this scheme, as it is very much based on the decay in space. If you want to develop like another type of inner-outer scheme, so that it could apply to dispersive, for instance, equation, one needs to rewrite completely almost from scratch, right? From this point of view. Actually, if you look at the papers of Merle and Raphael, and and the student, where they construct blob solution for Fugitive Equation, they use a similar scheme, but the way they estimate is very different. Very different. It's much more energy type estimate and dispersive type estimate, I should say. But with this one for parabolic problems, it works very well. So, well, I think I'm going to stop here. Thank you very much. I think I have thank you slide.
Thank you very much, Yannick, for the beautiful talk. Any question?
Yeah, sure. So, can you hear me?
Yeah, I can hear you.
Yeah, okay. Thanks. Sorry.
I don't know who it is, but I can hear you.
Okay.
Yeah. Sorry, I was like on another pan. I didn't see the whole everybody, so I didn't see you speaking. Yeah.
No worries. I just wanted to ask how stable these examples are if you perturb the initial data a tiny bit.
Okay, so yeah, so this is the stability. It's one has to be. I didn't study the stability, even the linear one for this one. So I'm not able to tell you. I suspect that. Yeah, so let me think. So for the harmonic map flow, okay, so for the standard one, they, in that paper, they have like, I think, a stability result. Mm-hmm. Sorry. For mine, for the thing I presented here, I don't know.
Okay.
I don't know. It's already quite hard for the harmonic map heat flow. Huh? Mm. I think that, yeah, I mean, like, I think they have a stability result, but I don't, the analysis is quite, it's going deeper. Yeah, they study also a set of initial data for which indeed, like, you can construct this type of solution and so on. So in my case, I don't know. This is like we build one data, and now out of the blue, I cannot even tell you what is the linearization. I mean, like the Morse index of the linearization. So yeah, I would need to check that.
Okay.
Yeah.
Thank you.
There is like a problem when you look at harmonic maps. A lot of things depend on the degree on with which you are taking your bubble. Okay, so the degree is this quantization here, parameter M. So which is in my case, of course, I changed notations. It became a D in between. So the stability, if you are wrapping around a lot of times, then you are affecting very strongly the Morse index. So I just
analysis.
Yeah, it depends on the degree, I think. Yeah.
Okay. Thanks.
Other questions? Well, if not, Yannick, thank you very much for the beautiful talk.
Thank you. Thank you for the invitation.
Thank you, Yannick.
Well, and good luck.